Okay, so the proof is going to use our notion of labeled abacus. Okay, so recall that we had this notion of labeled abaci, and that was essentially a shorthand or pictorial way of thinking about what the terms that you get in the alternants are. Okay, so let's prove the Pieri rule. So I'm going to prove the rule in the form that I stated it, that S lambda hk equals something. Okay, so let's consider this. So let's look at S lambda times hk. Okay, so let me assume that n is more than the length of lambda. So that my claim is that this is equal to, so this is the claim, right? We're trying to prove S mu of x1, mu being those special, the description of mu as given in the theorem. Now observe, we can assume that length of lambda, assume without loss of generality that the number of variables is at least the length of lambda. Okay, why? If not, then both left hand side and right hand side are 0. Okay, otherwise the sure function S lambda is 0, and any S mu that can potentially arise on the right hand side will have more parts than lambda for sure, right? So both sides are 0, and of course the equality holds. So we'll assume that we have at least those many variables. Now observe that S lambda multiplied by hk, so I'm just going to use x now as shorthand. So observe, this is what we know, it has n variables, and what's the degree here? The degree is d plus k, okay, where d is the degree of S lambda. Okay, why is this? Because hk is just the homogeneous, the complete homogeneous symmetric function of degree k. So of course it's got of course it's got degree k. Okay, so the product has degree d plus k. Okay, good. Now what does that mean? That means, from what we just proved previously, that every symmetric, and it's symmetric of course, so any symmetric polynomial in n variables of a given degree is necessarily a linear combination of sure functions of that degree. Okay, so this can be written as some linear combination of C mu S mu. Now what are the mu's that appear here? They are just, mu's are just partitions of d plus k, okay, with at most n parts. So the at most n is okay, good. Now what does this mean? This means, as we said earlier, when you have sure functions, the key thing is to just convert it into the corresponding alternate. So let's just multiply both sides by multiply both sides by the Van der Waals. A delta of x. Doing that will convert S lambda into A lambda plus delta. We'll convert the right hand side into A mu plus delta. Okay, we'll run over all mu's in P d plus k. Okay, now what is it that we needed to prove in order to prove our original theorem here? Right, what we are trying to calculate is, what are those coefficients C mu really? So our job finally is to show that the coefficient C mu in this expansion is either 0 or 1. Okay, C mu is 0 for most of the mu's. It's 1 exactly when mu's of this special form. Okay, that mu contains lambda and mu minus lambda is contained in the horizontal shadow of lambda. Okay, in other words, mu minus lambda is a horizontal strip with k boxes. Only for those guys the coefficient is 1. For all the other mu's the coefficient is 0. That's what we need to prove. Okay, so let's see how shall we prove that. Let's see what this coefficient C mu is. So observe, C mu is nothing but the coefficient of a particular term on the right hand side. It's just the coefficient of x to the mu plus delta on the right hand side. Okay, we have used this argument before. The alternate a mu plus delta is the only one which contains this particular monomial x to the mu plus delta, and it contains it with coefficient 1. Okay, so it's the coefficient of this on the right, on the RHS, but therefore that's equal to LHS. So C mu is nothing but the coefficient of x to the mu plus delta in the product A lambda plus delta times HK. In other words, this is a particular coefficient in the product A lambda plus delta times HK. Okay, so what we'll do is to try and understand this product better. So that's going to be our main goal. Once we understand this product better, we can extract the coefficient that we require. Okay, so let's get down to business. So how does one understand this product? And that's where the abacus comes in. So let's do the following. So recall, going back to the lecture when we talked about abaci and so on. What's this A, in general, if I have a gamma of x. So we said it was a determinant, and you could rephrase it by saying that it's a sum over all A which were labeled abaci with bead positions being given by lambda plus delta. Okay, you run over all labeled abaci, and to each abacus we associated a sign and a weight. Okay, the weight was just that monomial x1 power something, x2 power something, and so on. The sign was a sign of the permutation in some sense. This was our notation. Now observe that if you are going to think about this product A lambda plus delta times HK, then what are you dealing with? Okay, now recall what HK was. Okay, so this is A lambda plus delta. HK is actually the sum of all monomials whose total degree is k. Okay, what is alpha 1, alpha 2, alpha n? Alpha here, alpha is just the tuple multi-index. Whose total sum is k. Okay, you have to run over all possible such multi-indices. Okay, now let's use the equation that's just above. We will rewrite this therefore as the one hand A lambda plus delta is the sum over labeled abaci and the second term is the sum over all x to the alphas, where alpha runs over multi-indices of total weight k. And now this product, therefore, what will the terms in this product look like? Okay, that's going to look like the following. It's the sum over all A and over all alpha. It's a double sum, if you wish, of sine of A, weight of A times an x power alpha. Okay. Now, what is this weight of A times x power alpha? What does this mean? Right. So, if you recall how the weight of an abacus was defined. So, let's go back to that. So, how does one define the weight of an abacus? So, we had an abacus itself was sort of a number line. with some bead positions. So let's say the beads reside at position 0, 2, 5. So that's where my bead positions are. So I have 3 beads in these 3 positions. Okay, and they are labeled by some numbers, by some x's, as we said earlier. So this is, let's say, bead x3, x2, x1. Okay, suppose this is my labeled abacus. Then what was the monomial, what was the weight of this abacus? This was just the following. It was x3, well, let's maybe look at this. It was x3 power 0, x2 power 2, x5 power 1. Sorry, x1 power 5. Right? That was the weight of this abacus. Just look at what bead resides at what position, and you just say, okay, it is that bead label raised to the corresponding position. Okay, now so that's on one side, and on the other I want to take this monomial and multiply it by x power alpha. Okay, now what does x power alpha look like? It's some x1 to some alpha 1, x2 to alpha 2, x3 to alpha 3. Okay, now what does that mean? The final answer therefore is the following. It's x1 power 5 plus alpha 1, x2 2 plus alpha 2, x3 its original position 0 plus alpha 3. Okay, in other words, what I'm doing here is just moving each of my beads, right? So I move my bead by alpha 1 positions to the right. I move this, I don't know what alpha 2 is, somewhere alpha 2 positions to the right. This moves alpha 3 positions to the right. Okay, so you should think of this multiplication by a monomial x to the alpha as performing the following operation. You take the original labeled abacus, take the beads, and you move each of them by alpha 1 spots, alpha 2 spots, and alpha 3 spots to the right. Okay, so that's what this multiplication is. So this new abacus, so once you do this, the abacus changes, right? So the new positions, so this guy x1 now is here, x2 is here, and the bead x3 is here. So that new abacus that's in green, the 3 green beads, that abacus I will call as the original abacus A translated by the amount alpha. Okay, so that's the name I'm giving the green abacus. These 3 beads together, I will call it the new abacus A plus alpha. Okay, so what's the summary of this discussion? So I'm just saying, summing overall A and overall alpha, you've got the sign of A, and weight of A times x plus alpha is just another way of saying take the new abacus A plus alpha and take the weight of that new abacus. Okay, so this is really what we are doing when we are computing the product of A lambda plus delta times the hk. It's got, even this product has the following abacus interpretation. Okay, good. Now let's look at what happens. There are actually 2 interesting things that can happen, and you can sort of already see it a little bit in this picture. So let's draw the picture again. Now so I have my original abacus with some bead positions. Okay, so let's say the leftmost bead is at some position. So I don't care what the label is at the moment. So the next bead is somewhere. So this is a certain labeled abacus. There are some labels. Okay. Now what am I doing? So let me do the following. So this is my original abacus A. Okay. Now to this abacus, I'm going to add an alpha, right? I'm going to give each of my beads some amounts of, I have to move them so many spots to the right. So this may be some x, I don't know which x, this is the very first one. So now I give this some alpha, alpha 1 or how much ever it is, alpha I. So let's maybe we should give this a name. I guess you can't escape that. So let's say this first guy was xi. Okay. Now let's say I gave it, so therefore I, when I translate it by alpha, I give it alpha I units of energy. Maybe I move it so many spots to the right. Okay, the next fellow here is maybe an xj, and I give it some number of units of energy. Maybe it goes and lands here. Okay, so this is my new position. Okay, and now the next guy is, so maybe let's look at case 1. So here are two cases. So let's look at the simpler case first. So here's the thing that can happen. When I give this some energy, xj goes and lands here. Okay, I take the next fellow, I give it some energy, it goes and lands here. I translate this some number of steps to the right, it goes and lands here. Okay, so what have I done? I've given each of them some displacement. I moved all of them to the right, but here's what happened when they moved. When I start from left and keep moving, it turns out that there are no collisions. Okay, so this picture that I just drew is a case where this process of translating, when I go from the original abacus A to the new abacus A plus alpha, okay, when I translate, the process does not involve any collisions. Okay, so each yellow bead moves some number of steps, but it doesn't hit the next bead. Okay, then I go to the next bead, I move that some number of steps, but it stops short of wherever the next bead is, and so on. Okay, so this sort of moving without collisions is one case. That's a nice case. Okay, now here's a picture of a case with collisions. So what else, how else can things go bad? So again I draw the same thing. Here's my abacus. So observe whether or not there will be a collision depends on both what the original abacus A is as well as what my alphas are, right? Alphas tell me how much I should move to the right. Okay, now here's an example of a case with collision. So maybe the first bead there is no collision, it's all right, comes here. But if the second bead is moved to this position, for example, then there is no way of doing this. So how will I, if I think of my abacus as just having a single runner, so I translate this bead, I keep moving it to the right, and it somehow has to jump over this guy and get to that position, right? So this is an example of a case where I have a collision. Okay, in the earlier one there are no collisions. Each bead I can move nicely to the right. Here the first bead is okay, but the second bead, when I try to move it, it goes and collides against the third bead. Okay, so I can't move it without somehow jumping over the third bead. So that sort of thing is a collision case. So here there exists a collision. Okay, so it's enough if there is a single collision. I already consider that as a bad case. Okay, no collisions is going to be my very nice case. So there are two cases. So when A goes to A plus alpha, it results in at least one collision, or the case 1, A goes to A plus alpha, does not result in any collisions. Okay, now why are we so worried about beads and collisions and so on and so forth? That comes from the following statement, which is a rather beautiful statement. So here's a beautiful observation. And of course, if you have seen things like the LGV lemma and so on before, it's not so surprising. But here's the observation here. So it says, so let's do the following. Let's take all labeled abaci A and all alphas, okay, which occur in the expression that we considered earlier, which is you take the sign of that labeled abacus and you take the weight of the abacus A plus alpha. Okay, this sum, if you restrict it Okay, don't just look at all the don't look at all the pairs A's and alphas which appear. So which pairs am I looking at? I only want to look at pairs A alpha which collide. Okay, A alpha with collision. I look at pairs in which there will be a collision. So these are pairs, colliding pairs if you wish. Okay, pairs with collision. Then if you only restrict to that subset of pairs, then the answer is a 0. Okay, so here's the key observation. If you take that sum that we were computing earlier, which means remember A is all labeled abaci whose beat positions are given by lambda plus delta, and what is alpha? Alpha is all possible multi-indices whose total sum is k, right? So that was the thing we were looking at. And then we said, well, there are, when you look at A and A plus alpha, the changing from A to A plus alpha, that movement sometimes produces collisions and sometimes doesn't. Now what we are claiming is, if you only restrict to those pairs A alpha where a collision happens, then that subset of pairs, the total contribution to the sum is actually a 0. Okay, and this happens because there is cancellation. Okay, remember sign is positive and negative. The claim is they will all cancel perfectly and end up giving us a 0 at the end. Okay, so let's prove this, that colliding pairs will finally give us a 0 contribution. Proof of this beautiful observation is the following, that if I give you a colliding pair, so suppose A alpha is a colliding pair, then what we can do is we can use this to manufacture another colliding pair. Okay, then there exists another, a different, okay, there is another, when I say there is another, I mean a different one, not the same as the original, another colliding pair, A prime alpha prime is not the same as A alpha, okay, a different one, such that the following happens. Number one, the final abacus position is the same. A plus alpha is the same as the final positions of the beads, A prime plus alpha prime. But the signs are opposite. Okay, and now you can see that this automatically implies the original statement we wanted to prove, that the total sum is 0, because to each colliding pair A alpha we are associating a partner A prime alpha prime, such that they have the same final abacus, final positions, which means the weights are the same, but the signs are opposite. So there's perfect cancellation. Okay, such that this is true. Okay, and how are we going to manufacture it? It's actually a very simple prescription. So how do you manufacture A prime alpha prime from A alpha? So let me just explain it pictorially again from using the same sort of thing we did earlier. So look at the pair A alpha. So here are my original bead positions. Okay, the beads are residing there. Now what I do is I have my alpha, and as I said, some of the, so let's look from left to right. So when I move these beads, maybe the first few beads don't result in collisions, but I have assumed that my original pair is a colliding pair, so there exists at least one bead which has a collision, right? So this bead here has to go past the bead after it, right? So this collides and then has to jump over it and go to some new position. Okay, and then look at what the next bead does. So now focus only on those two beads. Okay, so now let me focus, put a boundary around those two beads. Okay, so this guy was, let's say, an xi. This is the bead with the label xj, and xi goes to xi plus alpha I, and xj, I don't know where it goes. I mean, it could go past where the earlier guy lands, or it could go inside. It doesn't really matter. that goes to some position xj. Okay, so I'm focusing only on the two guys, the very first occurrence of a collision. Okay, now what I'll do is the following. Let me label the final position. So this is the final position of xi, and this is the final position of xj. Okay, now what we'll do is we will construct a new abacus as follows. We just take the same as the original, except we interchange the positions of the balls xi and xj. Okay, or if you wish, we interchange the labels of xi and xj. So what does that mean? So here's my, so this is my original abacus A. Now here's my new abacus A prime. It's going to have the same beat positions. All the other beat positions are the same. Okay, these are the same, but this particular beat here, the xi, what I'll do is I'll place a beat there, but I will label it xj. Okay, remember this is a labeled abacus, so I'm going to put xj in that position, and wherever I had an xi initially, I'm going to put an xj. So wherever I had an xj, I'm going to put an xi. Sorry. So this is my new abacus. Okay. Now what else do I need? I need my new positions. Remember, the final positions a plus alpha and a prime plus alpha prime has to be the same. So after I move them, I should get the same answer. Okay. So how will I ensure that? So all the others are the same, by the way. So I don't change any of the other beats. I keep all the rest the same. Only these two I interchange. Now I should also change my alpha. Okay. So how am I going to change my alpha? I sort of know where I need to land. Right. So remember, in the original, this is where the new xi lands. This is where the new xj lands. So I know my new landing position. So this is where I would like my xj to land, and this is where I would like my xi to, this is where I want my xi to land. This is where I want my xj to land. Okay. So that tells me what my new alphas should be. So I define alpha prime j as follows. So this is my, this much is going to be my alpha prime j. Okay, it's the amount which will carry my bead xj from this new position here to the desired position there. Similarly, what should be my xi? It's, what should be my alpha prime I? It's whatever it's required to take xi from this new position to the desired end position. Okay, and all the other data is fixed. Okay, don't do anything to any of the other alphas. So if this is node xk, I keep this as xk. If this is some number alpha k, I keep this the same number alpha k, and so on. All the other data I keep fixed. I only change xi xj and the corresponding alpha I alpha j's. Okay, and the prescription is easy. I interchange xi xj and I change alpha prime so that my landing positions are the same as for a comma alpha. Okay, so this is actually the original what I have described for you. Therefore, is given an a alpha, how to transform it to a prime alpha prime. Right. So the entire prescription has been given. Okay. Now comes the interesting thing. So observe that if I had started, so there are. So let's call this map something. I'll call this map phi. Okay, which associates to each colliding pair a alpha, it associates another pair a prime alpha prime. Now here are the observations. Okay, number one, if a alpha is colliding, then a prime alpha prime is also a colliding pair. Okay, that's clear, because you can see the collision is already happening at the jth place, right? This has to go past xi, because that's where the landing place was. Okay, the landing place of xj was beyond the original place of xi. Okay, so this is definitely a colliding pair. That's statement number one. Now let's see what statement number two. If you start with a prime alpha prime as your abacus and multi-index, then you apply the same algorithm. Okay, this is a colliding pair after all. So I can ask, okay, if I start with this colliding pair and if I try to find its partner, okay, I do the same thing. I scan from left to right. the first collision, whichever I see, I swap the two xi's. Now observe, when I do that, I will of course get back A alpha, because the operation was very simple. Look for the first collision and swap those two guys which are colliding. Okay, so if I start with A alpha, I will get A prime alpha prime, and then starting with that A prime alpha prime, I will get back A alpha. Okay, so this is what you would call an involution. If you do it twice, you get back to the original. And here's the key, the punchline, that the sign is of course interchanged. That is the whole point of performing that interchange of the xi and the xj, because then if you go back and see how the sign of an abacus was defined, it's just a sign of the corresponding permutation formed by the xi's. And here I'm just interchanging one pair, and so of course the sign is going to become negative. Okay, so what does that do for me? It proves the observation that I made, that the sum over colliding pairs is going to give me a 0. Okay, so which means, what's the corollary? So this proves, this is the end of the proof of that beautiful observation. So now what does this prove for us? It says that A lambda plus delta of x, hk of x that we were trying to compute, it's okay to throw out the colliding pairs. Okay, you can run it over all pairs abacus A alpha which are non-colliding. Okay, and what is this? Sign of A, weight of A plus alpha. Okay, and what did we need to do? We needed to figure out what is the coefficient of a given monomial x plus delta in this, x to the mu plus delta in this. So recall, we wanted to compute coefficient of a particular monomial x to the mu plus delta in this, in the left hand side, therefore in the right hand side. Okay, good. So now that's almost done, because let's again ask ourselves, how can you get that particular monomial, right? So let's draw the abacus again. So here's my abacus. So what is x to the mu plus delta? So let me mark those positions. Okay, and so on. So this last guy is mu1 plus delta 1, mu2 plus delta 2, and so on, dot dot dot, mu n plus delta n, let's say. Okay, so in this case, say n is 5, so I'm only looking at 5 beats. So these are the positions on which I want my 5 beats. Okay, so that's what it means to say if I am looking for the coefficient of x to the mu plus delta. Okay, in fact I know which beads I want, I know the bead labels as well, right? Because what does x to the mu plus delta mean? So recall, x to the mu plus delta is just nothing but, let's write that down, it's x1 to the mu1 plus delta 1, x2 to the, and so on. So in other words, I have to put x1 here, x2 here, and so on. Excellent. So I want to put those beads. So the beads actually have to appear in their natural order, right to left, x1, x2, x3 till xn, and they must be located in positions mu1 plus delta 1, mu2 plus delta 2, and so on. Okay. Now this is the final abacus that I'm interested in. Okay. So the question is, for which a's and alphas can a plus alpha give me this abacus? So that's my final question. So this is the abacus I want. Right, so what should we call this? Maybe something B. Here's my abacus B, and now the question becomes, for which A alpha is the abacus A plus alpha equal to B? Okay, and for which, what sorts of A alphas? We are only looking for non-colliding A alphas, because we've already said the colliding guys we can throw out. So you're looking for non-colliding pairs such that after you translate, it gives me the final the desired abacus B. Okay, so what is this? What is this condition? What does it mean? So it means what could A have looked like, right? So again, let's draw the original A. Okay, so observe that since A alpha is non-colliding, it means all the beads just moved to the right without having to jump over any beads. So in the final answer, x1, x2, xn occur in this order, means that in A also they must have been in the same order, right? There's no other way out. So one thing we know for sure, in A, the beads must have looked like this. So this guy is bead xn followed by bead xn minus 1, xn minus 2 and so on. So they must have occurred in the same order. Okay, and there should not have been any collisions, right? So which means when I move this by some alpha n, the final, where it was initially plus how much ever extra movement I gave it, it should not go past the position of the next beat, which is xn minus 1. Okay, so observe that the original positions of, in A, I know what my original positions were, right? My bead positions, because A was a labeled abacus with bead positions given by lambda plus delta. That was my original. So this bead is actually in position lambda n plus delta n, right? So I actually know the bead positions as well here. So let's write that down. This guy is actually at position lambda n plus delta n. Okay, and the bead is labeled xn. Okay, so this is sort of bad notation. I should have just labeled the bead. So this bead is labeled xn minus 1, xn, and the bead positions themselves are lambda n minus 1 plus delta n minus 1 and so on. So those are the bead positions. Okay, now the point is, when I keep giving it an alpha n, it shouldn't go past the next guy. So what are my conditions here? So let's just do the most general condition. So if I had xi, so this is bead xi plus 1, this is bead xi, right? And we know their positions as well. This is lambda I plus delta I, lambda I plus 1 plus delta I plus 1. So what we know is the alpha I plus 1, the amount of movement there doesn't get it past this. So the condition here, the non-collision condition, says the following: lambda I plus 1 plus delta I plus 1, that's the original position, plus the extra movement doesn't get you beyond that, shouldn't even collide, right? So this is less than or equal to this minus 1, so that there is no collision. So this is the non-collision condition. And if you sort of see what that means, so observe delta I plus 1 is actually the same as delta I minus 1. Okay, just by definition. So what this implies therefore is that lambda I plus 1 plus alpha I plus 1 is at most lambda I. Okay, so that's the condition on the alphas. So we sort of figure out, this should be true for all i's. Okay, in other words, remember the alphas are telling you how many positions to the right you're allowed to move. So it's saying you can allow, alpha I plus 1 is at most lambda, it's the difference between lambda I and lambda I plus 1. Okay, good. So now if you go back and see what this implies about the mu itself, so what this says, so observe lambda I so if you see finally the beat positions, what are the final beat positions? If I take A alpha, for which A alpha am I going to get this equal to B, right? And what is B? B is the abacus with mu n plus delta n and so on. So in other words, this should be beat position lambda plus the alpha. Similarly, and so on, dot. This guy is the original position plus my alpha 1. Okay. So what does this say? This just says that the mu's, if you sort of stare hard at this, the delta cancels throughout. So what this says is that the mu's are just lambda plus alphas. Okay. So observe lambda I plus alpha I is the same as mu I. That's the other thing we know. This is the other statement. Okay. So now putting all this together, what this says, so putting these two facts together, that each alpha I is bounded by the difference of successive parts of lambda, and the lambda I plus alpha I is mu I. Okay. So if you now put these together, you will see our horizontal strips making an appearance. So what this says is, here is lambda 1. So this is a Young diagram of lambda, lambda 2, lambda 3 and so on. So what it's saying, the condition here is, to each lambda, whatever alpha you add, the new part is mu. Okay. But that amount that you add is at most the difference between the two successive parts. Okay. So for example, alpha 2 is at most lambda 1 minus lambda 2. So which means how much I add here is at most the difference between the one part above and this one. In other words, this is the maximum I can add. Similarly, the alpha I can add to this is maximum this much, because it's the difference between lambda 2 and lambda 3. Okay, the first part of course is a exception. There is no condition. I can add alpha 1 can be anything. Okay. The last guy, there is a condition again, that at most it can be this much. This is the maximum I can add there. Okay. So these conditions here, these two conditions exactly mean this. So these two conditions, if you think about it for a second, say exactly this, that mu is a partition which contains lambda, and mu minus lambda is contained in the horizontal shadow, is so what I call is a horizontal strip. Okay. And further with k boxes. So that's the other thing that's also clear from what we have been doing, that remember we said the S mu's which appear have k boxes more than the original lambdas, because the degree of the right hand side is degree of lambda plus degree of S lambda plus a k. Okay. So so finally this is the end of the proof. So in some sense, this horizontal strip condition is just the same as a non-colliding condition, saying that whenever you have a bead, you move it to the right, it doesn't collide with the next bead. Okay, this guy, you move it, it doesn't collide, and so on. So that non-collision is just saying that, these, when you try to expand the lambdas along each row, the expanded row should not go beyond the position of the next row. Okay, this expanded guy doesn't go beyond also. So that's really the end of the proof. So we'll look at various corollaries and so on next time.